Before we can continue our study of linear systems, we first need to review eigenvalues and eigenvectors from linear algebra. First, we need to look at what it means for a matrix to be in RREF form. So we take M by N matrix, call it A, is said to be in row reduced echelon form, or simply RREF, if it satisfies four conditions. The first, all 0 rows, if there are any, appear at the bottom. The second, the first non-zero entry from the left of a non-zero row is 1. Third, for each non-zero row, the leading one appears to the right and below any leading ones in preceding rows. Finally, if a column contains a leading one, then all other entries in that column are 0. If the matrix satisfies properties 1 through 3, then the matrix is said to be in row echelon form. Or simply REF. We need another definition. An elementary row operation. On any matrix A is any one of the following. Type 1 is to interchange 2 rows. Type 2 is to multiply a row by a non-zero constant. And type 3 is to add a multiple of a row to another one. These are the three types of elementary row operations. Let us now look at how to put a matrix into REF and RREF. So starting with the REF process. We need to start by looking in the matrix A for the first column with a non-zero entry. This column is called the pivot column, and the first non-zero entry is called the pivot. What we're going to do is we're going to suppose that the pivot column is column J, and the pivot occurs in row I. Interchange rows 1 and I if necessary. This will give us a matrix B. The pivot is now B1J, which cannot be 0. Now multiply the first row of B by 1 over B1J. This will give us a matrix C. Now, we note that C1J is now guaranteed to be 1. If CHJ for 2 less than or equal to H less than or equal to M is not 0, we're going to add negative CHJ times row 1 to row H. And we repeat for each H. It now follows that the elements in column J in rows 2 through M are 0. We're going to denote this matrix D. Now what we do is consider the m minus 1 by n matrix, call it a sub 1 of D, obtained by deleting row 1 of D. We're going to repeat the above procedure. On A1. If we now continue in this way, we will get a matrix that is an REF. To put a matrix in RREF, we start by putting it in REF using the process that we just described. We're going to denote this matrix by H. So suppose that rows 1 through R of H are the non-zero rows. And that the leading ones occur in columns C1 through C sub R. This would mean that C1 is less than C2, which is less than C3, so on and so forth, and CR would be the largest. We will start with the last non-zero row. So we're starting with row R. We will add suitable multiples of row R to all rows above it to make all the entries in the column CR above this leading one zero. Repeat this process for rows R minus 1 through row 2. This will make all entries above a leading one equal to 0. This will now result in a matrix in RREF. So we're now going to define eigenvalues and eigenvectors. So let A be a n by n matrix. A number lambda is said to be an eigenvalue of A if there exists a non-zero solution vector K of the linear system A times K is equal to lambda times K. This solution vector, oh dear, vector, is said to be an eigenvector corresponding to lambda. Now we can write this linear system in the form of lambda in minus a times k is equal to 0. This will have a non-trivial solution if and only if the determinant of lambda in minus a is equal to 0. We call this the characteristic equation of A. The eigenvalues then are simply the roots of the characteristic equation. Once we find the eigenvalues, we can find the corresponding eigenvectors by solving this linear system using RREF. And we'll take a look at finding eigenvalues and eigenvectors next. Let's consider the matrix. 1, 2, 1, 6, minus 1, 0, minus 1, minus 2, minus 1. And we'll go ahead and find eigenvalues and eigenvectors of this matrix. So the first thing we need to do is we need to find the determinant of lambda I minus this matrix A. So this will be lambda minus 1, minus 2, minus 1, minus 6, lambda plus 1, 0, 1, 2, and lambda plus 1. The determinant winds up being lambda times lambda squared plus lambda minus 12. And that has to equal 0. This will give us solutions. Lambda 1 is equal to negative 4, lambda 2 is equal to 0, and lambda 3 is equal to 3. So we have 3 eigenvalues. For the eigenvalue lambda equals negative 4, what we're going to do is we're going to take lambda. So negative 4, everywhere there's a lambda in the above matrix, we put negative 4 in. So this will give us the 3 by 3 matrix, negative 5, negative 2, negative 1, negative 6, negative 3, 0, 1, 2, and negative 3. So this reduces to the matrix 1, 0, 1, 0, 1, negative 2, and 0, 0, 0. Interpreting this, this will give us that x1 is equal to negative x3, and x2 is equal to 2x3. This means that x3 can be any real number we want. Set it equal to 1. I don't like the way that looks. Then lambda 1, our first eigenvector, will be negative 1, 2, and 1. This is capital lambda. We're going to repeat the process for the other two eigenvalues. So for lambda is equal to 0, we'll get the 3 by 3, minus 1, minus 2, minus 1, minus 6, 1, 0, 1, 2, 1, which reduces to 1, 0, 1 over 13, 0, 1, 6 over 13, 0, 0, 0. Which will give the system x1 is equal to negative 1/13, x2 is equal to negative 6 over 13. Again, each one times x3. So x3 can be any value we want. For convenience, let's get rid of the fractions. We'll make x3 negative 13. And so lambda 2 will be 1, 6, negative 13. Finally, consider the eigenvalue 3. We'll have a 3 by 3, 2, negative 1, negative 6, 4, 0, 1, 2, 4, which will reduce to 1, 0, 1, 0, 1, 3 halves, 0, 0, and 0. Which gives us the system x1 is equal to negative x3, x2 is equal to negative 3 halves x3. So we make x3 equal to negative 2. And we get our third eigenvector to be 2, 3, negative 2. Let's now look at the 3 by 3 matrix. 9, 1, 1, 1, 9, 1, 1, 1, 9. And we'll determine eigenvalues and corresponding eigenvectors for this matrix. So again, first thing we want, determinant of lambda I minus A. So it'll be the determinant of the 3 by 3 matrix, lambda minus 9, negative 1, negative 1, negative 1, lambda minus 9, negative 1, negative 1, negative 1, lambda minus 9. This determinant will be lambda minus 8 times lambda squared minus 19 lambda plus 88. And that has to equal 0. So we get the solutions lambda 1 is equal to 8, lambda 2 is equal to 11. For lambda is equal to 8, we'll get the 3 by 3, where every entry is negative 1. which will row reduce to 1, 1, 1, and then 2, 0 rows, which says that x1 is equal to negative x2 minus x3. So here we have two independent variables. So let's first set x2 to be 1, x3 to be 0. This will give us the vector negative 1, 1, 0. Now we can set x2 to be 0, x3 to be 1, and this will give us negative 1, 0, 1. So in this case, an eigenvalue gave us two corresponding eigenvectors. So now let's look at the eigenvalue 11. This will give us the 3 by 3, 2 minus 1 minus 1, minus 1, 2 minus 1, minus 1, minus 1, 2. This will reduce to 1, 0 minus 1, 0, 1 minus 1, 0, 0, 0, which is the system x1 equals x3 and x2 equals x3. And so, we'll get an eigenvector 1, 1, 1. That concludes this lesson. I hope you've learned something, and we'll see you in the next one.